Hello, my name is Ben Fulroth, and the title of my final project is Improving Deep DTA, a published deep neural network model for predicting drug target affinity using a modern dataset in model fine-tuning. So just to give you a little background, I've been a scientist for over 20 years, and at a very high level, one way in which drug discovery can occur is shown here, whereby on the left-hand side, we screen a lot of molecules, anywhere from hundreds to even billions, depending upon the test that you design. We typically put our compounds into plates. We also have a lot of robots and automation that can move the compounds from one place to another, and ultimately to test those compounds to a target protein of interest. I'm showing one example of a protein in the middle panel, which is called KRAS. KRAS is implicated in cancer. A mutation in KRAS can cause it to basically signal downstream for the cell to divide continuously, and that can create cancer. So what we'd like to do is develop a small molecule, such as those shown here in color, that can bind and therefore put KRAS into a conformation that shuts it off. And so one way we can do that is to be able to see if a molecule binds, and one parameter that we can calculate that's an inherent property of the small molecule in the target protein is what is called the dissociation constant, or KD. We can get to the KD as shown on the left-hand side, where basically we increase the concentration of the compound that we're testing from low to high. Then we plot that concentration on the x-axis versus the response in the particular assay on the y. We take the 50% line on the y-axis and then draw a perpendicular line to the x. And from that, we can determine the dissociation constant. And this is a really important characteristic of the drug-target interaction, as it allows us to rank order the compounds. So then we can go back and do some tweaking of the molecule, retest, and hopefully in an iterative fashion start to improve the molecules. And so moving towards this final project, what really interested me about this particular paper was that they basically showed that they developed a neural network model that was able to predict KD from just the SMILE string of a particular drug and the protein sequence of the target protein of interest, which I thought was really cool and could be a really useful tool for us at my current company. And so just a little bit more information about SMILEs and proteins and how the paper actually uses these. SMILE stands for Simplified Molecular Input Linear Line Entry System, which is a mouthful. At the end of the day, it basically is a way to formalize the encoding of the atoms and bonds of a molecule into a character string. So taking this particular drug, we can encode it into this string as follows. In a similar way, we can do the same thing with proteins. Proteins can be represented in single amino acid with their single amino acid abbreviations as American alphabet letters. And so if we take KRAS, for example, we can represent that with this following sequence of letters. One interesting thing about this is that the protein sequence does not encode the 3D nature of a protein, which I thought was quite remarkable, that the model is able to learn the representation of the SMILE string as well as the protein sequence without the information about the protein structure, which is quite amazing. So how does this actually work? And so the model or the paper basically showed that they take the SMILE strings as shown on the bottom left here. They then created a mapping and went to great lengths to prove that their mapping was correct. But they basically map each of the different characters in the string to a number, and therefore if you take the sequence and pass it through the map, you can produce this array of numbers up at the bottom. In a similar way, you can do the same thing with the protein sequence as shown on the bottom. You pass it through a mapping which maps each letter to a number, and you can produce the same type of array. You can then feed each of these through the neural network as shown in the middle. And so with that background in mind, thinking about this final project, I'm very practical. So I asked myself one question, and it came in the form of, how can I make this model more useful for my team? And so I thought of many ways, and two ways really surfaced. One is, could I train it on a more modern data set, a more diverse data set? The paper was published in 2018. The data sets that they used to show that their model was working were published before that in 2011 and 2014. Lots of things have happened in drug discovery since then. So I wanted to see if I could make this model better by training it on a more modern data set to be more applicable to current day drug discovery. In addition, I also wanted to see if I could fine-tune the model to a more specific task, more specific and relevant to our group, and that is predicting low affinity fragment-like drug precursors. And I'll have a lot more to say about this on later slides. And so the first thing I wanted to do was to see if I could reproduce what the model published before I started to experiment with the two questions that I had. And so I downloaded the model's code and their model, and I quickly found early on that all of their code, their model, as well as the data was all wrapped up into five-fold cross-validation, which was surprisingly hard to pull apart because it was all interdependent and reliant on each other. I had to do this because the training time was just too long. If I left five-fold cross-validation in place, it would have been, I think I calculated, about 100 hours of training time on my local machine. I did move to Paperspace, but even so, the training time was just too much. So I was able to pull apart the model and the code, remove the five-fold cross-validation, and move on to the two data sets that they basically showed that their model was working. And the first was called KIBA, which stands for kinase inhibitor bioactivities. Some information about this particular data set is shown on the left. In terms of the training, I was able to successfully train the model and reproduce what they published. On the left-hand side is the loss, and the loss that they used was mean squared error, as it's a regression problem. In addition, they also used a metric called the concordance index. A concordance index of 1 is the best you can get. 0.5 is basically 50%, or basically no better than random guessing. And concordance index of 0 is basically the worst you can get, or basically opposite of what you want. And so as you can see, we're able to get fairly decent concordance index values. Looking at the table of values at the bottom, where I have the publication values in the first row and my values on the bottom row, you can see that my values match up very nicely with theirs. In addition, I took the first 100 predicted values from the test set and plotted those as a function of the actual true values on the x-axis, and came up with a nice positive correlation with an R-squared score of 0.73. I then moved on to the second data set that they published on, that their model was working with. And so this particular data set I was more interested in because they basically report the same metric, or the same parameter for affinity, KD, that we normally report in the same units. So it made it a lot easier for me to think about how I would transfer this model to our data. The composition of this data is a little smaller than the previous. However, when training, we get about the same results. And so the loss looks great. The concordance index checks out. Looking at the table below, I'm able to match up, and even best in some cases, what the model actually published on. So pulling apart the model, the code and everything, removing the five-fold cross-validation didn't seem to really affect the way the model was trained. In addition, similar to the previous data set, I plotted the actual values, the first 100 values of the test set, the affinity values, versus the predicted values, the model predicted values. And as you can see, we have a nice R-squared score of 0.94. So in conclusion, I felt fairly comfortable moving forward that I was able to validate the model. And so I moved on to the two questions that I proposed at the beginning. The first one was to be able to modernize the model, train it on a more diverse and more relevant data set in terms of drug discovery today to make it more useful. And so in order to do that, I spent a lot of time searching for data sets, stumbled upon bindingdb.org. They made it very easy to download all of their data into a TSV file as shown here. In addition, it was very large. So 2.7 million rows of data, 1.2 million compounds, 9,000 targets. So very large, hopefully very diverse. I found early on lots of data wrangling was needed in order to get this particular data set in shape and in the format that the model could be used for training. At the end of all the data wrangling, I ended up with about 16,700 unique drugs, 1,400 unique proteins, protein targets, about 31,000 interactions. Moving on to training the data, as you can see in a slightly misleading way, it looks like the training loss on the left-hand side, the green trace is decreasing. However, if you look at the scale in the very top left corner, 1 times 10 to the 13th, so astronomical MSE. I tried a lot of different ways to troubleshoot this, but at the end of the day, I could not seem to train this model on this new data set. I have a lot of ideas as to why this is happening, but unfortunately, due to limited time, I could not explore these, but I'm still very interested in this problem. In addition, the concordance index is right around 0.5, so no better than random guessing. So from that, I moved on to my second question that I wanted to explore, which was, could I fine-tune the model to a more specific task of predicting low-affinity fragment-like drug precursors? So just a quick primer on fragment-based screening. It's a proven strategy whereby instead of screening larger molecules, you screen smaller molecules, as shown on the right-hand side. The idea is that these smaller molecules, as you can see, can find all of the little nooks and crannies of a protein much easier. And once they do find those nooks and crannies, if you're able to detect them, you can then elaborate those molecules, make them better, find better interactions. So they just represent better starting points for drug discovery. And so some characteristics of fragments, they're usually less than 300 Daltons. One disadvantage is that they're usually very low affinity, and so you have to have really nice, expensive instrumentation to detect them. So with that, I thought it would be really nice to have a model that could predict the affinity to kind of steer you in the right direction. So in order to explore fragments, I needed to first wrangle the data and basically filter out all of the molecules that were too large. And so I was able to do that with a package called RDKit. I then moved to the model, whereby my strategy was to take the Davis trained model, which I previously showed performed very well on the Davis data set. My next strategy was to freeze the first few layers of the model. This came from exploring and reading the documentation, the TensorFlow documentation, that basically stated that the beginning layers of a model are really responsible for learning the fundamental features, in this case, the SMILE strings and the protein sequences as they relate to affinity. And the later layers are more geared towards a higher level learning, higher level tasks, hopefully more specific tasks like what I'm interested in, detecting weaker compounds to target proteins. And so once again, I trained the model. Again, misleading, but the error or the MSE is astronomical. Lots of troubleshooting on this, but at the end of the day, I could not seem to get the model to learn. In conclusion, and I apologize, I'm running out of time, but I learned a lot. I was able to validate what the paper published. And I've got a lot of ideas on how to move forward. So I thank you for your attention, and good night.